Hello, everyone. Great to see everyone here. All right, to start my talk on our work on PIR, it's worthy to go over the background, a short background on homomorphic that we'll need, so I'll start from there. So homomorphic encryption is basically a method is a form of encryption where you can perform computation on your data while it's in encrypted form. So the way it would usually work is you have access to some basic operations, additions, multiplications, and then you can build more complex functions from there. But the thing you have to keep in mind is that, first of all, multiplications are more expensive than additions when you're using homomorphic encryption. For example, as the numbers shown in this table, they can be up to 20 times slower. And the second is that the multiplicative depth of the circuit that you want to evaluate can determine the parameters of the homomorphic encryption system. And that, in turn, determines the performance of the homomorphic encryption system. So the two considerations to have in mind is, first, you want to use as few multiplications as possible, and the second, you want to reduce the multiplicative depth of the circuit that we're evaluating as much as possible. So with those two, we can dive into equality operators, which is the first building block of our work. So just so we're on the same page on definitions, an equality operator just takes two inputs. If they're a match, it outputs 1, and otherwise it outputs 0. So this is an important building block for a lot of secure computation protocols like PIR, PSI, and whatnot. So the equality operators that exist would typically work over a bitwise representation. And for example, we have the plain or the arithmetic. In the plain, we're comparing an encrypted number with an unencrypted number, whereas in the arithmetic, we're comparing two encrypted numbers. So if we were to analyze these with regards to the constraints I mentioned about homomorphic encryption, we can see that the arithmetic operator performs 2L multiplications for a number of length L, a bit length L, and does this with a multiplicative depth of log L plus 1. So the number of multiplications and the multiplicative depth both depend on the bit length, which kind of limits the scalability of this equality operator and how big of a number we can compare. So we probably need a better approach. So now we can dive into our construction, which works over constant weight code words. So first, what are they? Constant weight code word essentially means that it's a binary string where the number of bits set to 1 is exactly k. So the example on the right is 6-bit numbers with only 2 of the bits set to 1. So how would we be able to compare constant weight code words? So first, in the plain case, we have an encrypted x with an unencrypted y. So we see the bits of y, so we simply take the bits of x corresponding to the bits of y, which are 1, and simply extract those, multiply them, and there will be exactly k of them because of the fact we're using constant weight code words. We multiply them, and that will give us the result of the comparison in encrypted form. In the arithmetic case, where both x and y are encrypted, it's a little bit more complicated. First, you perform this inner product between the bits to get this value c in encrypted form. Now, c is something between 0 and k because both of x and y were constant weight. C is something between 0 and k. It's k if they were equal and they were a match. It's k if it's anything less than k, it was a non-match. So just translating what I said into a formula, it's that thing on the bottom right, and that will give you the result of the comparison in encrypted form. All right, so what would it look like if we evaluate these? So starting off with the plain, comparing the plain constant weight with the folklore plain, you can see that based on the numbers in the green, the plain constant weight operator is like up to 10 times even more faster than the folklore operator, shown in the red on the top. And this could be attributed to the fact that first of all, we're just performing less multiplications and less expensive homomorphic operations. And second, due to the fact that we have a smaller multiplicative depth, we can use smaller parameters in some cases, and that also makes things faster. Now, there must be a catch. The catch is that we're not using the most efficient representation for the number. It's a little wasteful. So this comes at a higher memory usage. The representation is a little bit larger than it could be. But that's not set in stone because we can actually use a more efficient representation as shown in the numbers in orange, so it will do slightly worse for runtime, but it would also alleviate the burden on the memory and on the size of the elements. So we kind of have this freedom to choose here. So now for the arithmetic operators. So here, the runtime, like there isn't the massive speed up as we had in the plane. So the numbers are more comparable, still better as the greens show, but not insanely like better as before. And this can be attributed to the fact that the number of operations in the number of operations in the arithmetic the number of operations in the arithmetic are not as little as they were in the plane. So, but that is not entirely going to be a problem, as we'll see in a bit. The other thing is that the multiplicative depth of the arithmetic, again, solely depends on k, the weight of the strings. So that allows us, in some cases, to use smaller parameters, which benefits us, which helps the runtime. Now, like I said, the number of multiplications in this case is still high, but all I mentioned up till now was only using a single thread. But if we were to parallelize, we could see that we could get the massive advantage that we had in the plane. And this is because just the fact that the arithmetic operator has all these operations that can be parallelized. So as you can see from the lines on the top, the constant weight operator has a very massive speed up, maybe can be sped up like by a factor of 10, whereas the folklore operator shown in the blue on the bottom can get at most 2 times faster. So there, with that, we get back into the realm of being like 10 times faster than the folklore. All right, so we have an equality operator now. We can think about building a PIR protocol from it. So just to jog everyone's memory, a PIR protocol is a protocol where a user wants to retrieve an element from a database such that no one can figure out what element is being retrieved. So there is, for PIR, you could be in the single server or multi-server setting, depending on whether one or multiple servers are holding the database. We're focusing on the single server setting here. And then there are variations based on how you're going to retrieve or refer to the element you're retrieving in the database. So in the index PIR case, you refer to your element as an index in a neatly structured table, whereas in queried PIR, you have this space or you have this domain of keywords, and you want to refer to your element via a keyword in that space. So for example, that could be the domain of keywords could be 265-bit 256-bit identifiers, or some file names. Now, like up to now, index PIR has seemed to be the easier case, and there's been a lot of work on it, like SEALPIR and MulPIR, and this structure over the database actually helps. Whereas queried PIR has been kind of the harder one ever since it's been proposed. And then the solutions that kind of existed were mostly in the form of just reducing queried PIR back to index PIR via some extra round of communication, or which would come at some probabilistic chance of failure, whereas we wanted to find an approach that didn't have those caveats. So for our protocol, the way it would work is that you have the user that has a query from this space of keywords that it wants to retrieve. So it encrypts its query, sends it over. Now, because of the fact we have a fast equality operator, the server simply compares the user's query to all the keywords that are actually in the database, not with all of the keywords that are in the domain, but with only the keywords that are actually in the database. So it performs those comparisons and then multiplies each of those. So that will give you a vector of zeros and ones, and then you multiply that selection vector into the actual data corresponding to each keyword, and then you just sum them up kind of like an inner product, which will give you the record that the user was looking for in encrypted format, which you send back. So in the evaluation, the observation was that this form of performing PIR using equality operators performs better and is more advantageous as the domain grows larger and larger. So in the case where the database is dense and it's very similar to index PIR, there are very fast state-of-the-art solutions, but as the database grows sparser and sparser, and we approach queried PIR, those solutions won't stand much. So that's where constant weight PIR can kick in. So this can be attributed to the fact that if you were to count the number of particularly homomorphic operations you're doing during the protocol, you can see that the number of operations that previous protocols perform in the main part of their protocol actually depends on the domain that you're operating over, so like the 256-bit identifiers. Whereas in constant-weight PIR, the number of operations actually depends on just the elements that you actually have in the database. So that's why sparsity in the database makes constant-weight PIR perform better. Now, we're using this representation for these keywords, and we have all this focus on multiplicative depth. Now, the analysis shows that because we have this focus on multiplicative depth, if you were to aim for a very specific multiplicative depth for some purpose, in this case PIR, you can see that the representations that we are using compared to the representation that the previous PIR works have used, our representation is smaller for the same multiplicative depth. If you take one of these graphs, for example, the one on the left, you can see that the red trend being the representation size that we're using compared to the blue, which is the representation size that the previous work was using. You can see that the constant weight representation is consistently smaller for a given multiplicative depth. All right, so to kind of finish off, the final aspect that I want to talk about in which constant weight PIR is beneficial is when we are returning larger responses to the user. So we have to work in this in quantized ciphertext in PIR. Now, if the response is larger, if the records that the user wants to retrieve is larger than one ciphertext, you would have to send multiple ciphertexts. So previous work, when you wanted to do that, for each ciphertext you wanted to return, you would probably have to redo the whole protocol. Whereas in constant weight PIR, you can do the bulk of the computation up front, and then each ciphertext that you want to send back is just a marginal cost, which is shown in the red graph, which is constant weight PIR that grows slower compared to the blue trend, which is some of the previous work. So if you're returning about 250 kilobytes of data, at that point, it's good to use this form of PIR using equality operators. All right, so to wrap up, I introduced constant weight equality operators, which are suitable equality operators to use with homomorphic encryption, and are much faster than the existing equality operators. And then using that, I introduced constant weight keyword PIR using equality operators, which performs PIR in a single round, is faster for sparser databases, essentially keyword PIR, and is faster when the response size is large. So our code is also available on GitHub. I invite you to take a look and run it for yourself. And yeah, I'd be happy to take any questions. Thank you.